Thank you, Mary. So, first of all, I would acknowledge the help of many colleagues who supported this project, which already goes on for several years. So, oops, this doesn't work. So here you have an overview of my presentation today. After an introduction, actually as an introduction, I would like to perform a simple acoustic experiment with you, as you will see in a minute. And then basically I have three main parts. I will introduce all the acoustic systems that have been in use or been developed over the last about 2 decades. Then there are two main parts. First, I will discuss about the experience on calibrating such devices for bedload flux. And the last part will focus on identification of grain sizes. Okay, so here you see the setup of this acoustic experiment. And actually, when I said I will perform this experiment with you, it's not quite correct. Please, Carlos, my colleague from WSL and PhD student, Carlos will actually perform the experiment, and your role as an audience is has more a passive character. It's a little bit like, the passive acoustic monitoring system. So I would like you here, actually, you see here, the setup here, it's just on the screen enlarged, but Carlos will now perform the experiment. So you see 5 quartz spheres of different size, and he will first start with the smallest one and let it drop on all the other bigger spheres, and then he will go on with all the spheres, only letting them drop onto the larger spheres, and finally he'll take the large one and see what happens. So your role basically is you should listen. What do you hear? How does the tone pitch change with sphere mass? And maybe you have some other conclusions. Please, Carlos. Okay, thank you, Carlos. So that's it for the moment. I will come back to this experiment in the second part of my talk towards the end of my presentation. Okay, so now a short overview over the acoustic measuring systems that are being used right now. So here, first I introduced the Swiss plate geophone system. Basically, we use a standard size steel plate, as you can see here. The dimensions are given here on top. And we fix from underneath a geophone sensor, which you can see here. Actually, we don't use this spike here, but we unscrew the spike and use the hole here to fix the geophone sensor from underneath into this aluminum housing, which provides watertight protection for the sensor. And maybe another detail you can see here, we also use here elastomer elements in order to acoustically isolate each plate from the neighboring one. And on the left-hand side, you see just one example of installing these plates. The simplest possibility actually is if you have a check dam with a certain drop height where you can simply fix a steel structure here on the downstream side. Actually, what you see here on this diagram is the response characteristics of this sensor, and basically this sensor which we use is more designed to pick up signals in the lower frequency range. Now, here you see a typical signal on the left-hand side, and I have to say that in the past we usually do not store or record the full raw signal, because this for a long time was not really feasible. So we have developed some procedures of pre-processing of the signal, and we actually only store a limited number of summary values. One of these values is explained here. So basically we define a threshold voltage output, which should sort of guarantee that we don't pick up the noise, and we simply count the number of events when the signal exceeds this threshold value. And apart from this, you see here some other summary values which we use. We also recorded the integrals under the signal. In later applications, we use the square integrals, thinking that this summary value could tell us something about the energy that is delivered to the plate with this technique. And we also record the maximum amplitude. Okay. Now, one, of course, important question with these techniques is what is the minimum grain size that we can detect with such a system? And you see here the result of some flume experiments, which show you a few things. First, you can see that the rounded particles tend to produce more impulses, or the probability that we record a signal. That is, means here probability that we exceed this threshold level of 0.1 volt. Whereas the flat grains produce less signal, or the probability is smaller. Then you can also see some differences depending on the size or the weight of the particle, and also if the particles move in clusters, so there are multiple grains, this will also change the probability of detection of impulse count. And actually, further flume experiments and also the experience from our field observations, they tell us that the triggering and the number of impulses we count depends on grain size, grain shape, type of movement, number of grains, and grain velocity. So now the other system for which quite a number of investigations have been made in the past, both in the flume and at the field, is the so-called Japanese hydrophone system. So basically the main difference is here a steel pipe is used as the impactor element. You see here two examples. The steel pipe typically is buried halfway into a fixed structure of cement or concrete on a sill, for example. And you see here the dimensions. It's important to note that the mantle thickness is much smaller than what we use for the Swiss plate geophone system. Then here a microphone sensor is fixed at one end of the pipe, and the pipe is air-filled. Now, here I would like to mention that they also use a kind of counting a number of peaks, so to say, but in this way of analyzing the signal is different from the one that I've shown you before. Actually, first, with a procedure, you know, the envelope of this raw signal is determined, and then actually, again, the number of peaks of these envelopes are counted. So it's a little bit different way than what is done for the Swiss plate geophone system. Then here you see a number of other systems. I won't go into detail about all of these systems, but I just want to show you what have been used in the past. So basically, you see most of these systems, they are impact plate systems with the plate flush with the bed, except for the system number 4 here. And as you can see, basically the dimensions of the plate are different, and in some cases also the sensor is different. For example, here an accelerometer is used in these systems here. Actually, to summarize, the first system has been partly calibrated in the field, but primarily for grain size identification. I will come back on this later. The second system here has also been calibrated in the flume only. The third system here we have to distinguish. The small plate has, to my knowledge, not been calibrated. The large one, there have been some efforts with flume calibration. And here, actually, these flume experiments, they showed that the system allows the counting of the number of grains, and there is some indication that also grain size may be detected or identified. Okay, so I'll leave you here with these explanations about all these systems and go on. So the next type of sensors that have been used in the past in quite a few studies are the so-called underwater microphones. Actually, they are called hydrophones in these studies, but I tried to make some distinction to the Japanese hydrophones. That's why I call them here underwater microphones. You see here, this system that has been employed in the United States was calibrated with, I think, Halley-Smith type direct bedload samples, and this other system here has been compared to geophone measurements in the Drau River in Austria. I will come back to that later on. So now I go on to the next part, to the determination of bedload transport intensity or flux. And actually, we have most experience with this system. We have gathered in this so-called bedload observatory at the Ellenbach in Switzerland. We have now more than 20 years of measurements with this sensor here or a similar sensor. And for the last few years, we also have these 3 metal baskets installed here at the large check dam, so we can take reliable direct bedload samples and compare them with the signal of the geophone plates. Actually, this system during the last 1 or 2 decades has been employed in quite a number of streams with different characteristics, primarily in Central Europe. There is also one application at the Elva River in the United States and one at the Naal Eshtamoa in Israel. And at most of these sites, actually, there is at least a possibility for calibration. And at some of these, or many, there have already been some calibrations efforts have been made. Here you have some pictures illustrating some of these sites. So actually here in these 2 Austrian streams, a kind of upscaled Halley-Smith type sampler is used, here with a metal pillar to guide the exact positioning on the bed just downstream of one of the metal plates. Here you see the result of calibration for bedload flux, which we performed at the Ellenbach stream in Switzerland. You see here the gray circles, they refer to the basket measurements, and the red squares here, they refer to the measurements of sediment volume in the retention basin. Basically, both these 2 different groups of data, they suggest that there is a linear calibration relation between number of impulses and bedload mass. You can see here that there is some offset between the basket sample measurements and the retention basin data. We cannot yet really explain this difference quantitatively. We have some ideas and hypotheses, but we have still to check. Here you see a comparison, a similar representation of number of impulses of the Swiss plate geophone system against bedload mass. And you can see that for a number of streams, we also obtain fairly good linear calibration relationships. Now, I'm moving on to the Japanese pipe hydrophone system. And you see here calibration efforts have also been made in a similar way. Particularly, there's been quite a number of flume investigations, but here I only show field calibration data. Basically, the conclusion here is that you can also calibrate this system. What they have found, however, with this system, that depending on bed load transport intensity, a different channel output is more suitable than another channel. Basically, what this means here, different channels are more or less comparable to the analysis of the Swiss plate geophone system by choosing different threshold levels. So it's a little bit similar. And yeah, you can see that also the quality of the calibration relationship varies here from site to site, of course, and also to some degree on transport intensity. Here you see actually another comparison, and this data here refers to measurements that have been taken at the Swiss Erlenbach stream for 3 different types of sensors. In red is the Swiss plate geophone system. You see here the number of impulses over time. Here is one flood event with bed load transport. You see the discharge here, the blue line. And actually, for the analysis here of the Japanese pipe hydrophone system, we use the same procedure as for the Swiss plate geophone system. And you can see that actually the output or the level of impulses is quite comparable. What I should also add here is that for the Japanese pipe hydrophone system, we tried here also a variant in that we did not only install the pipe, which had a length of 1 meter, covering the same width as the metal basket, but we also used this, what we call here plate hydrophone, and actually it produces quite a comparable signal as to the pipe hydrophone. But the advantage of this variant here of the system is that it's more robust in high energy environments. Now, going on to the underwater microphones, I show you here some calibration efforts of an underwater microphone. You see here the situation, how it was installed into the Douro River at this point. And actually here there is a sill which is equipped with 40 geophone plates and sensors over the entire width of the stream. And you see the results here. So basically, the 2 systems appear to provide quite similar measurement in terms of bed load transport intensity. What you see here is the hydrophone signal, the root mean square of the signal, and here is the geophone signal on the abscissa, and it's simply a slightly different representation here. And you can see there is quite a good correlation both with all the geophones, but the correlation is somewhat better if you only consider the nearest 3 geophone plates for comparison. So calibration appears to be possible for rivers with limited turbulent noise. This is one conclusion of the groups that have studied the performance of this system. We can also say that the main challenges with this system is that the hydrophone signal depends on the location of the bed load transport activity, and generally the integration area is unknown and probably also quite difficult to determine. Okay, so my last part will deal with the identification of grain size with such systems. And here you see the results of calibration measurements in 3 streams with the Swiss plate geophone system. And you can see that there is some general trend of a dependency of the maximum transported grain size a correlation with the maximum amplitude of the signal during the calibration measurements. Of course, there's quite some scatter, but still it appears that this dependency, this functional relation is quite independent of sight. So now for our more detailed measurements at the Ellenbach site, based on this observation, we have now developed an approach which allows us to also identify grain size and finally calculate or calibrate the system in a different way. So as you can see here, the analysis is based on this correlation we have seen on the last slide. We also assume that every particle collides once against the steel plate, or I should rather say at maximum once. And the amplitude thresholds, which you see here as the dashed horizontal lines, they can be used to discriminate between grain size classes. So basically, we use these amplitude classes to extract or to determine how many particles have been transported within each grain size fraction. And you can see here the results. So basically we counted the number of particles that we collected with the bedload samplers. So here you see the result of calculating the number of particles from the signal, of course, after calibration, I have to say, for the smallest, the next particle size range, and so on. And yeah, there is over several orders of magnitude. There is quite a good correlation. And what you see here is now basically a comparison of sort of this simpler method, which I introduced first, simply correlating total mass with number of impulses. These are represented by the green diamonds here, whereas the other two, the blue and the red data, they refer to this amplitude histogram method. And basically, yeah, I forgot to mention that here with the blue procedure, we simply count the number of impulses in the way I explained first, whereas here, the red points, here we make sort of a similar assumption as for the Japanese hydrophone. We first determine the envelope of an impact of a signal wave or pattern that is thought to be due to one particle impact. So, but you can see they're quite similar, but what is important here is that particularly for smaller masses of bedload that we collected in the basket samplers, there is a clearly better agreement, but this also has, of course, to do because for the amplitude histogram method, we also used lower threshold values than the 0.1 traditional limit. Okay. What is also an interesting question, in fact, when using this system is something which is sometimes referred to as saturation of the system, particularly for the Japanese hydrophone system. So what you see here actually is sort of a schematic diagram illustrating the impact of 3 particles. But typically, if we were to use a real sample, the time intervals between the impact of the single particles would be much larger for our experimental conditions at the Ellenbach. So what we did here, we tried to see how much time on average is between 2 particle impacts. And this is here expressed by this parameter ZP, which gives the relative duration of time with respect to the total duration of the sample that was occupied by particles. And actually, what you see here is this relative time here. Actually, we obtain here also quite a good correlation with bedload transport rates. And what is also interesting here, if you look at the numbers of the relative time, so for our calibration measurements at the Ellenbach, we had at the most about 1% of the time was sort of occupied by a signal impact. So we are still quite far here from saturation conditions in this case. Of course, we also have flood events there, for which we may, of course, approach also saturation conditions. And actually, you can also use this approach to calculate or estimate total bed load transport. And again, we can see here that particularly for smaller masses of the bed load samples, there is a better correlation or prediction than for the traditional, very simple impulse mass-based method. Okay. Now, it's fine. Now I'm coming back to an impact plate system that was actually developed by a German Luxembourg group by Krein, Barrière et al. And they have recently shown they have actually developed quite a novel and interesting technique to reliably determine the frequency of what we may call here this again as a signal packet, which is due to one single particle impact on the plate. And actually, basically what this procedure does, it reconstructs sort of the original signal. It recomposes this by a number of different well-defined oscillations or sinus functions. And so they can, by doing this, they also use a library of different functions in the background to find the best, solution. And then they're interested in sort of the dominant frequency of the first peak. So that's how they determine a characteristic frequency of such a single particle impact. As you will see in a minute, we use a slightly different technique, but of course, one reason for searching for such a procedure is that if you apply a simple fast Fourier transformation, you may argue your signal is quite short because you don't know beforehand which signal packet belongs to which particle size range. Okay, here then are the results from this investigation. So apart from using this technique, they did a number of flume experiments, and what they found basically is that the size of the particle is reflected both in changes of the maximum amplitude of the signal packet and of the dominant or characteristic frequency of the signal. Actually, you see here the functional relationship, the empirical relationship that then they use then to estimate the D50 of their mixtures they have used in the flume experiment. Okay, so grain size identification is possible based on frequency and amplitude information is the conclusion. So now I have to speed up. We also now looked at the frequency information in the Swiss plate geophone signal. Basically what you see here, the green line is a theoretical line from a model proposed by Thorne some 3 decades ago, I think. And you see here the red points are some measurements from the group of Belady using an underwater microphone. And here the blue and yellow squares are from the actual geophone sensor at the Ellenbach. And what you see here, we used here 2 different methods to determine the frequency. One is very simple. It's based after we have identified the envelope. We simply count the number of excursions here, peaks, and divide by the time length of the packet. The other method we tested is to use a fast Fourier analysis by doing some pre-processing first. And there's quite similar results, but what you see here, there is 2 sort of problematic regions. Here, for the smaller grains, we tend to underestimate theoretical frequency, and we think this is a limitation of simply of the geophone sensor, which is not really designed to pick up high frequencies. On the other side, we see here there is also not really a big sensitivity of grain size on frequency, and we think this is limited by the steel plate mass. Actually, so I'm coming back to the initial experiment we performed at the beginning. So there is a theory of self-generated noise by spheres of different sizes impacting against each other. This is the simplified equation if you have two spheres of the same size. So I go a little bit quicker. This is the more complicated equation if you have spheres of different sizes. And basically, if you apply this, for example, to our conditions of the Swiss geophone plate system, you will see that you basically reproduce this green line curve for quartz material. But the interesting thing here is that if we use the mass of the steel plate in the equation for the larger sphere, then we can reproduce here this leveling off for larger grain sizes, what we have observed experimentally in the field. Okay. So this brings me to the conclusions and outlook. So here I've prepared a table summarizing sort of the main findings or possibilities that these different systems have. And to make also the story short of this table, I think that most of these systems can really be calibrated by the flume or field measurements. Of course, ideally you should use field measurements if we want to apply them in the field later on. There are still some question marks. And the second point is that it also emerges that certain systems or sensor and plate combinations, for example, are more suitable for certain particle ranges than other systems. These are sort of basically the two main conclusions. And you see here, these are the main conclusions for the impact plate systems. Then we have the conclusions for the Japanese pipe hydrophone system, which actually, I would say, we can summarize with similar words here, except that these pipes are, of course, less robust for high-energy environments. And that's why both Japanese colleagues and we have started to look at the performance of a so-called plate-type hydrophone. And here, some conclusions about the underwater microphones. I've mentioned these points before as well. And since I think I've exceeded a few minutes my time, I stop here. Thank you.
Thank you, Dieter. So our next speaker is Colin Rennie, and Colin's going to talk about acoustic devices, active acoustic devices for measuring bed load.
Thank you. Okay, so first of all, thanks to the conveners for the invitation. I was asked to speak specifically about calibration of ADCP bed load velocity, so that's what I'm going to talk about, and calibration to bed load transport rate, so converting a velocity measurement to a transport rate measurement. I should say that this talk is co-authored by the Reese team, so Demi introduced the Reese project. So Richard, Reese, James, and Murray are co-authors. And the reason is the main data set that I'm going to be analyzing is from the Reese River. So here's a picture of the Reese River. And what I've been interested in for the last few years is trying to understand the spatial distribution of bed load through a river like this. Now, conventionally, to be able to do measurements, to be able to understand the transport rate spatially, not just from the morphologic method, but I mean actual transport rates on the bed throughout the domain, I think the only conventional approach would have been using conventional samplers. And I think all of you know the limitations of these samplers. Bill, I think on your Mud Creek, you spent many, many, many days trying to get a spatial distribution using conventional samplers. So first of all, there's a lot of effort and labor. So it's very difficult to get real spatial and temporal variability. There's a physical problem that the sampler disturbs the flow field, and so there's many years of calibration efforts to try to figure out what the actual transport rate is based on a measurement of sediment into the sampler. It's very difficult to sample at high flows because you have to be on the river. So I've been in situations where I couldn't actually do the measurements because it's too dangerous, and it takes a lot of effort to do to actually process the samples. I might say, in case I forget, that for all the resamples, I have Murray to thank and his team at NIWA for actually processing over 100 bedload samples for grain size distribution, and this talk wouldn't have happened otherwise. So what I've been doing for the last few years is trying to use an ADCP to get measurements of bedload. So an acoustic Doppler current profiler, I assume most of you would be familiar with the technique, but the basic idea is it's an acoustic tool that measures water velocity throughout a column of water, and you can get velocities in bins below that system based on backscatter and the Doppler shift of backscatter of sound at each of those bins. Now, like I say, it's usually measured for water velocity. The estimate of the velocity at the bed can be used to measure the boat velocity. So you are collecting ADCP water velocities as the boat is moving. You need to know the boat velocity in order to get water velocities in a Earth coordinate system. So basically the frame of reference of the boat has to be removed. There's two ways to do that. You can measure the boat velocity by, say, GPS, or you can send another acoustic beam down to the bed and use it as a Doppler sonar. So that's called bottom tracking. The problem with bottom tracking in a mobile bed condition is there are particles moving along the bed, and the velocity of those particles will bias the estimate of the boat velocity. So what I've been doing is extracting that bias by comparing the bottom track velocity to GPS boat velocity and using that as an apparent measure of these particles, the velocity of those particles. So this is something I did for my PhD way back in 2002, and this talk is going to do a chronology of calibration efforts since that time. Okay? So some of these slides may be familiar to you, but when we get to the Reese, all of it will be new. I'll do a little bit of theory first. The ADCPs usually have 4 beams, and so each of those beams sends the acoustic pulse down to the bed. This is what the bed locations would be if the ADCP had a depth of 2 meters above the bed. And you can see that each of those sample areas encompasses a circle that is about the same as the depth. So the diameter of this sampling area is close to 2 meters. If you have an 8-meter depth, this is the circle, and the diameter of that circle is, again, close to 8 meters, 7.5 in this case. It, of course, depends on the angle of the beams coming out from the ADCP. The important point about this is you get only one velocity component in each of those 4 beam areas. So in order to resolve a Cartesian velocity, we need to take the one component from here, the one component from there, one component from there, and one component from there, put it through a transform, coordinate transform, and you can then get an estimate of x, y, and z velocity. With the 4th beam, we get 2 redundant measurements of the vertical, and that can be used to estimate error. Now, I've been talking about reflection off of the bed. In fact, the bottom track pulse has a finite length based on the duration of that pulse, and the sample area is really a volume, and that's because the backscattered pulse will be cut off or binned in the portion where both the leading and trailing edge of the beam are being sent back to the ADCP to record that pulse. And if that reflected beam is still coincident with the oncoming beam, then, or incident beam, if you want to use that terminology, then this location in black, any suspended sediments in that black location, the scatter off of those suspended particles will be recorded at the same time as scatter from the bed from this location, or that time. In other words, suspended particles above the bed can be interpreted as being coming from the bed. This means that suspended particles could be incorporated into the bottom track pulse, and therefore some suspension near the bed could be included in this estimate of bed load. what this diagram shows is the pulse progressing in time as it reflects off the bed. The maximum height off the bed where the sample volume can reach is approximately half of the pulse length. So the sample volume depends on the pulse length employed. For a typical RDI ADCP, it's 20% of the depth. That's the default pulse length. So if you're measuring in a 10 meter deep flow, the pulse length is going to be 2 meters long, means the sample volume could be about a meter off the bed. That's much larger than we tend to think of as bed load. But I would argue it's pretty much realistic for bed material load. And if you're in a shallower depth, the pulse length is usually closer to something that would be similar to a bed load sampler. And so in most shallower situations, this height is similar to a bed load height. But just a caveat there. One or two more theory slides, and then I'll get into some data. So this is a slide that shows what the backscatter intensity is for particles of different sizes. So this axis, and this is from Thorne as well, this is acoustic wave number times the particle radius. And this is the backscatter form function. You can see that the scattering increases and then goes pretty flat. And this region where it goes flat is specular scattering. It has a value of wave number times radius of about 2. And long story short, it basically means that particles of a sufficient size will backscatter with an intensity that's proportional to that size. Particles that are smaller will have less backscatter intensity than their size would suggest. So for a typical 1200 kilohertz ADCP, the cutoff is about 0.8 millimeters for a diameter, which is this point here. So any sands or smaller sizes will be scattered with less relative intensity than gravels for a 1200 ADCP. For a 3 megahertz ADCP, the cutoff is 0.3 millimeters, just for reference. Okay, primary difficulties. In gravel, the main difficulty is that we're measuring in 4 different locations. So think of the gravel transport slides that we saw this morning, the videos, very sporadic transport. Sometimes there's transport at one location, no transport at another location, different values of transport at the 4 locations. In other words, you can't rely on the assumption of homogeneity between the beams. You likely don't have the same velocity in each of the beam locations. If you go through this set of equations describing the x, y, and z velocities, that basically means there's going to be some error in your estimate due to the heterogeneity. In sand beds, the main problem is because you have a gradient of transport near the bed, in the near bed suspension layer, it's not exactly certain where in that suspended layer the bottom track signal is bouncing off of. So it could be that it's reaching down near to the bottom, and we talked a lot about what the surface layer was in the talk this morning. It could be bouncing off near the top if it's a densely concentrated layer. I've done some uncertainty assessment to try to figure out what errors can be involved. And rather than going through the whole slide, I just want you to focus on this one equation. So this would be the uncertainty of the bed speed. And it's a function of the error in the bottom track, error in the GPS, error in the compass. And if you're taking a single measurement at a single location as a representative of the mean, it will also rely on the actual true variance of the bed load, temporal variance. The bottom track error we can get from that redundant beam. GPS error I've obtained from my RTK system by doing some measurements of velocity of that GPS. Compass error depends on the degree of error in direction from the compass, as well as the relative velocities of the bed and of the boat from this equation. And lastly, I've used a bed load model, uncertainty model for that parameter. And long story short, in most situations for spatial surveys, the bed load is so variable temporally that this term dominates the error terms. But to give an idea of the degree of error, I'm going to focus on two data sets. The variance of bed load that I estimated was around 7 centimeters per second for the Fraser and up to 30 centimeters per second for the Reese. And this is due to the high transport rates on the Reese. In terms of the bottom track error itself, typical values were around 2 to 3 centimeters per second for the Fraser and around 7 centimeters per second for the Reese River. So when I show data near the end, you can think that the uncertainty of those measurements is around 7 centimeters per second. Okay, so let's go into some calibration efforts. This was the very first one done on the Fraser River gravel bed reach when I was a PhD student under the supervision of Mike and Rob Miller. We dropped the sampler, and I think Jeremy might have been on the bridge one day. You were, I think. We dropped the sampler from the bridge. So here's an example of how difficult these kind of measurements are. And we had the ADCP on a boat that was tethered to the bridge. Okay, and the Fraser River gravel site is up here on the map, Vancouver down here. This is one example of an hour-and-a-half sample in duration. Blue is individual 5-second ensembles of the bottom track velocity or apparent bed speed. And you can see that the average had a value of about 5 centimeters per second, but there's a tremendous amount of scatter. So individual samples have a large amount of error, but mean values may be meaningful. Those of you who use ADCPs, this is the bottom track velocity or the boat trajectory over that hour and a half. And you can see it looks like it went upstream over 250 meters when we know it was fixed in position. From the samples we were able to collect from the gravel river, we developed the first calibration effort, and the R-squared was reasonably good. The uncertainty was fairly large, particularly for samples of short duration. But this was the first indication that this method might be useful. So this is, by the way, transport rate is always going to be on the y-axis, the ordinate, and the bed speed is always going to be on the abscissa. Went down to the sand bed reach. This is the estuary for the Fraser. So these are a couple estuarine channels. And again, did the same kind of calibration effort. And here in blue is Canoe Pass, and in red is Sea Reach, so two different distributary channels. In black is the gravel bed data. And you can see that, first of all, there's different calibration relations for the two sand bed channels, and distinctly different for the gravel. Lessons from this were that you get different calibration for different sites, and it was probably due to the different grain size. Also, in more difficult sites, there were much larger dunes on Canoe Pass. The calibration can be weaker. So the next phase was to go into the lab. I went to St. Anthony Falls in 2006 and did some measurements in both sand and in gravel using both a 1200 kilohertz ADCP and a 600 kilohertz ADCP. The nice thing about the St. Anthony Falls lab is they'd set up bed load traps, and so I was able to get good measurements of the actual transport rate. This is one example time series from the fore and aft beams. So this is the beam facing upstream and the beam facing downstream. And you can see that as dunes passed, the same signal was observed in the upstream beam in red and then the blue downstream beam. So this shows that we're seeing dunes passing as they went into the bed load trap. And here was the calibration data set from all the samples we could collect. In black is gravel, and it was relatively weak, but still had some calibration. And in red was the sand. Again, we were able to demonstrate there was a difference between the two material types. There was also a much larger data set that looked at the frequency, and it depended on the operating frequency as well as the pulse length. And I won't show that. Dave Guyman did some work as well on sandbed Missouri River and the gravel bed Trinity River. He wasn't too happy with the calibration on the Missouri River, and he actually attributed that lack of calibration to the difficulty of sampling with bedload samplers. On the Trinity River, he divided the data set up into a sand component and a gravel component and showed two different calibration relations. And I'm going to follow that similar path on the Reese. Okay, so let's get to the Reese data set. There were a couple of motivations for doing this bedload sampling. You've seen from Damia this morning the morphological estimates that we've been doing. Well, we wanted to get a bedload transfer rate across the downstream end of the reach so that we could close that morphological budget. The other issue is, as I said, I'm interested in spatial distributions, so I wanted to be able to measure a spatial distribution, then convert that to a transport rate rather than just a velocity. So the first calibration effort, here's Murray with his Helly Smith sampler. I'm holding on to an S5 river surveyor, and in the first year we collected 40 samples. In the next year we collected 110. The first year of data yielded this calibration relation, and it was pretty interesting because the equation was actually the same as I got on the Fraser River for a gravel reach. But we then used that calibration relation based for a series of measurements that were collected along the downstream end, and here are those ADCP data. The green is the water velocity, blue is the bedload velocity. You can see that almost all the bedload was observed at these locations, which corresponded to a transport path eroding off of that bar. And using that calibration curve, I came up with an estimate of 2.2 kilograms per second across the section. But the question was, how reliable was that calibration? Because we didn't consider the grain size distribution of those samples. And we know that the Reese River has both sand and gravel in it. So for the next set of data, for this talk, we broke up the data into 4 different groups. Entirely sand, sand with gravel, and note that I'm using 0.6 millimeters as the sand cutoff. That's largely because it worked out the best statistically, but also because it's closer to the difference between specular and Rayleigh scattering for this particular instrument. Gravel with sand, and then pure gravel, so only less than 10% sand. Taking all the samples and dividing those into those 4 categories, and excluding any data that had relatively low percentage of good bottom track, this is that final calibration relation. So in green are all of the gravel with sand samples. In red is all the sand samples. Blue is sand with gravel, and black is gravel only. And on this plot, I've put both the Fraser and the Reese. So F is Fraser, R is Reese. And there are a couple of things that are nice about it. First of all, in data sets that have both Fraser and Reese data, they actually match. So that suggests that it's not site-specific, it's really only grain size specific, which means that calibration efforts that we've done on some rivers could be applied to other rivers as long as they have the same grain size distribution. So that's one positive outcome. The difficult part is that there's a huge amount of scatter on the gravel with sand relation, and so the R-square is relatively low. And secondly, there's a very large difference between the gravel and the sand. So on the Reese River, that means that we're going to need to know whether we have gravel moving or sand moving in order to apply this calibration relation. And that makes life a little difficult. I tried to break the sand with gravel relation, gravel with sand relation into subcomponents based on percentage sand. It works to some degree, but not well enough to come up with different relations. Okay, so what are the implications of this? Like I said, I'm always interested in doing spatial distributions. Here's an example of us doing a spatial survey across the main Anna branch. So we basically just drag the boat back and forth in really tight sections and collect bottom track data as we go. And this produces maps like this. So this is the same paper, Williams et al., that Damia talked about. Here are the velocity, depth average velocities from 5 different surveys collected over this flood cycle in 2011. You can see that there were a few peaks, one major peak in the flood, and we collected data with the ADCP at A, at B after the big peak, or on the falling limb of the big peak, C, D, further down that falling limb, and then at E, basically on the falling limb of the next major peak. So I've got the water velocity in the Anna branch from those 5 surveys, and here's what we're going to focus on, is the bedload velocity. I've used the uncertainty model to map where I'm confident that we actually had bedload during those surveys, and those locations are in yellow. So you can see that on the falling limb of the big peak, much of the reach was transporting, had high bed velocity, and was I have 95% confidence, actually 90% confidence, that it was moving. One of the interesting ones was the first survey here at A. You can see that the transport path was down this side of the bar and went into this second Anna branch. And in fact, during the main event, that Anna branch filled in, so there was no water in this Anna branch for the second survey. The air photo is from later on in the year. So we can use the bedload method to map the spatial distribution of bedload and try to see how transport of sediments causes morphological change like filling of this Anna branch. But how do we use the calibration to come up with an estimate of the actual transport rate? Here's a close-up of that first survey where the velocity, bedload velocity is coming down into this main Anna branch, secondary Anna branch. Based on which calibration relation we use, we can have estimates of the maximum velocity, which was 55 centimeters per second, could have been 0.6 kilograms per meter per second, or as high as 4 kilograms per meter per second, depending on whether we're using the gravel relation or the sand with gravel. That's a factor of 6 difference, and we have no real a priori method to know which one is the correct one to use. You could argue that in a low flow event like this, we probably have a bit more sand moving than gravel, but we actually could see gravel moving even at that lower flow. I think a reasonable assumption of bedload grain size distribution is thus required to constrain the transport rate estimate, and so I think you need to do some sampling in most situations. Okay, to summarize, and I know it's end of the day when we've all got jet lag, so I'm glad I kept on time. Calibration relations to estimate transfer rate from the apparent bed speed vary as a function of bedload grain size distribution, as well as operating frequency and bottom track pulse length. The calibration relations are improved significantly if you break the data set into distinct subpopulations based on grain size. Gravel bedload has much greater transport rate for a given velocity than sand bedload, and that makes sense just because the particles have greater mass. And I think you need an a priori estimate of which grade size distribution is in transport in order to choose which calibration relation to use. But I'll emphasize, I think the calibration relations may transfer from site to site. Okay, thank you.
Thank you very much, Con. So we have some questions. John, I think you were first with your finger up.
Dieter and Colin, thank you very much. We are located here at the DPRI, and they deal with disasters. And some of us are interested in floods. And some of us even think that most of the material moves during floods, and that much of the morphology of rivers occurs not in incipient motion, but during floods. Would each of you wish to comment on what you think in terms of your techniques that could be available? Because it's obvious that techniques change very rapidly with time, and back in 2007, we didn't think that we'd be as far as we are today. So obviously we've come of age in many things, but what about floods and measuring in floods? Thank you.
Well, I went first because I think my answer is quite simple. So, yeah, we have already had some discussion with authorities in Switzerland about using this system in the context of flood warning. I think at least qualitatively and also in terms of bedload transport intensity, it can be useful for flood warning. And actually, we have also one site where we have installed the system on request by a hydropower company, because they have had one of their water intakes partly destroyed due to a high bedload transporting event. They decided to build a gate there to close the intake in case of high bedload transport, and they installed some Swiss plate geophones as an alarm system.
Okay, so for the ADCP side, I think if you can get an ADCP into the river during the flood, it would work except for one caveat, which is high turbidity. So I've had some occasions where extremely turbid flow, the bottom track doesn't reach the bed and it doesn't work. So it depends on the nature of the flood. But if you're able to traverse the river by some means, either by boat or across a bridge or something like that during a flood, then it should be okay. Yep.
Helmut?
Helmut Habersack, Boca University, Vienna, Austria. John asked the same question I had noted down. First, I want to talk about our experience, because we were very excited to have different measurement techniques, let's say, deployed in some of the rivers in Austria, for example, the geophone plates. And then we had a very big flood in 2013, which was statistically maybe, I would say, a 200 years flood. And all the people that were paying for the installation were happy, because we said, now we have the first time for a very big flood bedload data. But we were totally disappointed, because I could show you the data, when there was an increase of the flood peak, suddenly and we had 7 geophones over the cross section, they stopped giving us any impulses, no impulses. So we thought, okay, now it's done, it's gone, or it's wiped out by the flood. That would be the even easier explanation, let's say, concerning the measurement technique, but it wasn't. It was still in place, and it started measuring after the flood suddenly again. So the only explanation we had so far was that it was a steep slope Urslau River, so we have there gravel dunes and gravel sheets in that case, I must say, that are on the way, and our belief is now that when it comes to a bigger flood and we have bed forms like we observed them at the Danube, we have gravel dunes, and we have just worked on this at a speed of 5.9 meters per hour. They are 11 meters long, 30 centimeters high, they move at a speed of almost 6 meters per hour. And when they are 30 centimeters high, the total signal, the vibration of the geophone of the steel plate doesn't work anymore. So unfortunately, I must say, due to our experience, that in alpine rivers down to the big Danube River, we must say that for the Danube we cannot use the geophones because of navigation restrictions, but we have this problem, and for the ADCP we also thought that we would like to use it, but there the same problem occurs like for the basket samplers with a rope standing on the bridge, as you showed, will not work in a real flood when trees are coming and it's too dangerous. So my fear is, and I want to listen to your advices, I think we are not capable now, at this stage with the message we discussed in this workshop, to cover real floods. And this is a big issue for us, because those people like Torrent Control, like Asabo dams here, they are interested in the real catastrophic floods, not in the initiation of motion and the medium floods. And also the Japanese pipe might get problems in a big flood by this dampening process or also by the physical damage. So I think we are still searching, at least in Austria, for some additional measures which can complement to those measurement techniques we have up to date. But flood measurement, I think, is not possible for real floods with these techniques in gravel bed rivers.
Just a comment. I agree. If you can't get the ADCP into the river, then it's not possible. Yeah.
Well, maybe also a short comment. I mean, I think that the problem which you addressed is the problem of sediment deposition, and we have had the experience in Israel with John Laurent that we had a comparatively weak signal there. We had also the hypothesis that maybe there was some partial deposition of bedload material onto the plates, and therefore also when we started with this technique, we said actually an ideal location is a check dam in a steeper stream, because this is a fixed point where you wouldn't expect any deposition. So in such conditions, I think it still works during floods as well.
That was exactly the situation what we have at Uslar. It's comparable to the Erlenbach, I would say, even from the size. So you wouldn't expect a deposition, a classical deposition, or maybe it's too deep, but it was a throughput of kind of gravel sheets which were moving through. So it's not a deposition, a static deposition on the plate, because it's this deep. It's also a seal, a bottom seal, a seal with 2 meters fall height, but it's more a transport of gravel sheets over this. And it's what we think it is. Maybe we are wrong, but yeah, it's something, it gives us some headache, I think, for the near future to discuss with.
Kimberly, I think you're next.
So I had 2 questions for Dieter, and the first one starts in a little bit of a statement. And when you said that you could figure out what size of particle was moving because of the amplitude rather than the frequency, I was pretty shocked. So that's my statement. But because I was thinking, wouldn't the amplitude depend on something having to do with a transport rate or hop height or something like that? And so my question is, why do you think that from one river to the next, that the amplitude of the sound captures the size of the particles? Do you have a hypothesis for that?
Basically, I think the impulse depends on the momentum of the impacting particle. So, I wouldn't claim now that we would expect the same relation between maximum amplitude and grain size for every site where we have measurements. I mean, we have just seen these 3 sites where it's more or less comparable. And my explanation that it's maybe quite comparable is I would think that probably the differences in particle velocity are probably less important than the differences in grain size, contributing to this, reasonable correlation we observe.
Oh, okay. Thank you. And then the other question I had was are you limited in the transport rate that you can, under which you can measure the size distribution? Because really, I'm thinking that you need to have individual grains hitting the plate rather than trying to read something about the particle-particle collisions.
Yes, well, I briefly mentioned this possible problem in terms of what is sometimes called saturation of the signal. So if you imagine you were to have multiple particle impacts at the same time or very close to each other, then you may have a superposition of the signal due to more than one particle. But as I've shown for the Swiss plate geophone system, for our calibration measurements at the Erlenbach, at least in the statistical sense, this was not a problem for the calibration measurements. Because we had at the maximum, we had about, during 1% of the time, we had really a signal due to single particle impacts on the plate.
Okay. In the front row.
Thanos Paparinkolau from the University of Tennessee. A question for both of you, and then a specific question for Dieter. So, despite of the criticism, I think there is a lot of progress that has been made. Is it fair to say that both techniques pretty much work well for low to intermediate flow transport rates?
Certainly it is easier with the ADCP at lower transport rates. Even without the high turbidity, if a large portion of the bed is moving sporadically, then the heterogeneity assumption or homogeneity assumption is problematic. And the bottom track tends to filter itself out. So at the highest transport rates, it is more difficult. But at the same time, if you discount the ones that are filtered out, it still gives a higher value. So I think you can still get some information out of it. Yeah.
Thanks.
For the passive acoustic measuring systems, I would say there is one similar point. So for lower transport intensities, yeah, you can better avoid this problem of saturation, which has apparently been some problem with the Japanese pipe hydrophone, because they also detect smaller grains than can be detected with the Swiss plate geophone system, so there's a larger number of grains and more impacts. On the other hand, for example, for our system, I think a certain minimum transport rate is better, because you tend to have larger particles that produce sufficient signal. But again, yeah, I would also expect that certain concentrations we might approach the saturation limit.
Right. So it appears that type of sediment and size of sediment are the two key sort of variables that dictate the effectiveness of both techniques to a large degree. And so my other question for you, Dieter, is regarding, vibrations of the plate and how, and in some ways that dictates if we can use, those plates for floods and so on. If we have come up with any ways of dealing with that.
Yeah, it's a good question. I don't know if I properly respond now to your question, but we have had some observation when we started with more systematic flume experiments. First, we fixed our plate sort of almost in the middle of the entire flume length, and we noted after some time that too much of the vibrations were transmitted from the entire flume that also started to vibrate. So in a second step then we sort of physically separated the plates at the downstream end from the flume. Another observation we have made is that, and this is a problem we have been facing now in the context of our objective to see whether flume-based calibration could eventually replace a field-based calibration. We have observed that we did not really get the same response, signal response, in the two systems, which is probably partly due to the fact that in the flume we had just one single plate with a steel frame, whereas in the field typically we have an array of steel plates embedded in a massive concrete structure. This may be one reason why we could not really obtain exactly the same signal response.
Right, right up in the back.
Hiroshi Suwa from Kyoto, belonging to University of Tokyo as a visiting researcher. I wish to make a question to Dieter. You showed a diagram relating the dominant frequency and the amplitude from the monitoring data of impacts or border. I think in such a case, from the monitoring data from Japan or from accelerometer attached to the impact plate, you may get a spectrum, power spectrum from the wave signal also. So the spectrum may contain much more information about the collisional processes information, I think. So if you use such data, incorporate such data, you may find much more information about the bedload, how to say, the motion. How do you think?
Well, I cannot really comment in detail on that because we only have started really looking at the spectral signature of these events. What we have found also useful, for example, is to see how much of the response may be due to just the water runoff when we have no bedload transport. But we haven't really done any detailed analysis about that. Maybe you could talk later to my PhD student, Carlos Weiss. He maybe have some more ideas on that.
Towards the Philippe, up the far corner, the man with his hand up. There we go. Great.
Philippe Beredi, University of Grenoble. I apologize in advance to make some advertisement, what could be an advertisement of the hydrophone system, but I want to complete the saying of Dieter and to answer a little bit to John concerning the floods. Especially the hydrophone system can be put aside on the bank under the water. And Dieter said that, this is a problem because it integrates a certain area. We don't know which area. Really, we have some ideas of the area, but this is really a benefit in the case of floods because you are safe in measuring. You put your device apart from the big velocity and above the water, the bed of the river, and then you get information of what is at 10 meters from the hydrophone. Concerning the quality of the signal, and it answers a little bit the question about the frequencies, really it works much better in large flumes for high water depths, and so for floods, because the frequency content of the signal is alterated when you have very low depths. And another issue that was mentioned in those questions is the use of the device in low flow conditions, and really then you get the beginning of transport. But with the inconvenience that it is, you don't really know the size because of low water depth, so the alteration of the signal frequencies.
Does anyone want to respond to that? Okay, right. Okay. Thanks for your comment, Philippe. This man here in the glasses, just beside you.
Yeah, just before that, one issue with the hydrophone at high flows, depending on the river you're in, you can have a lot of turbulence and air-generated noise. So maybe you could comment on that at some point.
Yes, I agree. And the next step is to use the hydrophone to eliminate the noise from the gravel bed, and then to use what is the other part of the signal to know a little bit more about the turbulence. But this is in 10 years.
My name is Tsubaki from Hiroshima University, Japan. So I'd like to confirm about the geophone. So the impact velocity, can we neglect some difference of the approaching velocity in the when estimating some sediment diameter? So the effect of the, can we assume that the effect of the velocity is minor? Is it correct? So I think you said so.
Yes, I more or less said so. I do not say we can completely neglect it. I mean, the important observation for us or for others so far was that there is some correlation solely between impact between maximum amplitude and grain size, and if it helps to identify grain size, I think that's fine. So of course, if you were to determine the impact velocity as well, you might even improve on that relation, but that is practically difficult, I think.
Okay, so can we obtain some information about impact velocity by carefully checking the frequency and some maximum amplitude or some integral of that? Can we obtain some information from that, or we cannot obtain from the signals?
Well, I don't know. We haven't investigated that, so it's possible, but I don't know.
I think theoretically that's possible, so I just confirm that you checked or not. Thank you so much.
Colin, do you have a question? You do, okay.
So a question for both of you, but first for Colin Rennie. Could we flick back a couple of slides?
Which one?
Keep going. Yeah, that one. Okay. Oh, okay. Yeah, that one I like. So I may be making this up, but I think Paul Carling told me once that when you measure bed load, if you get more than 1 kilogram per meter per second, there's probably something wrong, because that's about as much moving carpet gravel that you get through 1 meter bed width in 1 second. And it does look like there's a lid on there at about 10 to the 0. And if I think with Dieter's measurements too, you very rarely are getting more than 1 kilogram per meter per second bed width. Is that real, or is that something to do with the technique, or what are we to make of that? Or is it maybe coming back to Helmut's point that after that you start to get a moving layer, gravel sheets, those low amplitude Randy Deinhardt type gravel dunes, that means that it doesn't work anymore because now you've buried your sensor in not a moving carpet anymore, but an active layer.
So this is a good question. What I'm going to do is go back and look at the data that I filtered out because there was insufficient bottom track data, and see if any of those samples were greater than 1. I think it is a lid. I don't think there were many that were any higher. but I'll just like to double check.
Well, I don't know. And am I making that up, Paul, or did you tell me that once?
Well, I was a little bit surprised, but I don't remember.
And it's, I'll take the credit back then.
I'll just add, I think maybe an empiricism based on the work we did in the Pennines, but there did seem to be an upper limit in the Pennine streams, which were very similar in scale. And I wouldn't want to argue that there is an upper limit to how much you can get moving. You would possibly start collecting much more.
Maybe just to contribute, I just asked my colleague sitting here. We measure before the gradual sheets start, before we cannot measure anymore, let's say up to 5 kilograms per meter in second. So we have data to show you afterwards. So there's, for us in Austria, we have not a limitation by 1 kilogram per meter in second. Anyway, but it's but afterwards, yeah.
I think at this stage people are getting a little droopy, I guess. I might suggest that we continue the questioning perhaps after that session in the bar at dinner or tomorrow, but I think we should wind it up now. But I'd just like you to join me in thanking this afternoon's speakers. Yeah.
And I'd like to thank you for sticking it out to the end. So,